Um, cool. Okay, let's see. Just a quick tutorial here. So we've been going through, we've told you about what data exists, some of the ways to get at it. And for this topic, I want to actually start digging into, oh, I was going to take these headphones off. I was going to start digging into what, to actually playing with some of the data. And one of the things that's really about this SAR data, as we heard from Josh earlier, is that there's all kinds of things that impact the actual signal return you get. There's a number of factors related to the ground, the atmosphere, all of those things. Sometimes it's hard to use the exact, the actual full strength of the absolute amplitude coming back for useful results in the signal. But the one thing you can use it for really well is comparing a time series. And I think a lot of us have applications that look at a time series of RTC data, looking at changes over time. And so I'm going to give you one example of these. I know most of you probably aren't cryosphere scientists. You're not looking at snow melt on glaciers and in mountainous areas, but I'm going to present you a workflow that you can use to get stacks of RTC data and look at for changes in those data. And we're going to kind of go and play with a bit of that. So for my so for my talk here, it's going to be about specifically looking at snow on glaciers and mountainous areas. So right here, I'm kind of showing a bunch of figures. The top row are some time series of some locations of the VV image, the copolarized image, as well as the VH image, the cross-polarized image. And on the top row is just a bunch of images, and some of these are from different orbit types, different looks, different viewing geometries, but repeat orbits. And then in the bottom row, I've basically taken, collapsed them to say, what is the winter mean value when I'm looking at dry snow? And I've just called that 0. And I'm going to be using decibels in this talk as the unit, and collapsed them. And the kind of theoretical basis for what I want to show is that when snowmelt starts, there's a decrease in this backscatter. And so I'm showing 3 sites here. One is where there's snow covering bare ice on a glacier, and you see melt in this area starting in about April, and there's a backscatter decrease. Another one is snow that's higher up, and there's a backscatter decrease later in the year in more like July. You see a really pronounced decrease, and then the third image is somewhere even higher up, and this is a nice target that has this nice snow that doesn't actually experience melt in the summer, where you don't see that. So that's what we're going to be looking for in my workflow. And the region we're going to be looking at, we're going to be using Opera RTC data. So it's in what we call the Haze range, which is a part of the Alaska range. It's about 200 kilometers east of Denali. This is something you can find this data in Vertex. We're going to be getting at it programmatically in using Open Science Lab and the search APIs. Here's just a quick image of what the scene looks like. In the middle of the scene is the Black Rapids Glacier. It's flowing to the east, which then flows out into the Delta River, going north up to the Yukon, whereas the glaciers on the south side flow down and they reach the Susitna River here in Alaska. So anyway, kind of you can see some of this area. There's mountains, there's wooded terrain, there's some river deltas, there's a few lakes in it. Here's what these mountains look like. Here's from here in Fairbanks, from the Geophysical Institute where we work at. So you can kind of see these mountains. It's also, there's RTC data, Opera RTC data for these mountains going back through time, which is good, so that historical data exists, but I also like it because it's somewhere that, you know, I can look at and see. So with that, let's hop over to Open Science Lab, which I think I have to reshare this window. Okay, cool. So we'll see it. So we have the Jupyter book here that you all should have on the side. In the Opera data recipes, we're going to go to snow example. So if you can open this up, you're probably going to get a pop-up that's going to ask about which kernel you want to use. I have a whole bunch here, but we're going to pick the NISAR Early Adopters Workshop. And we're going to say yes here. If you don't see where some of this is on in your environment, there should be Jupyter Workshop, Jupyter Books. There's a folder, go to the main folder, and then Opera, Snow. There's a few more, but this is the most common, or the most up-to-date one. So I'm going to start. I'm going to run through some of the imports here. There's a couple functions that we're going to use that are going to be used for later. And then we're going to start. Also, one thing I want to note is that if you want to work on getting some of this data, there's data access recipes. There's a couple other these resources that Alex kind of had talked about some, but what I use is a little bit based on just the workflow presented in this notebook here of how to search and download Opera data. So definitely feel free to utilize some of those tools, but you're going to want to run this. So then you can check did my credentials work. Okay, they did. And then here I've set this up so it's going to ask you for the name of a directory. And this is just for this tutorial. You might want to think about other ways to set up your file structures when you actually work. I'm going to call this Haze. And the folder itself is going to go into just the root directory of your OpenSAR lab. So anyway, going on, we're going to want to get the data now. Here's just another image of this, the target area. So the main way that we're gonna do this is through this command here. We're setting up in this cell. There's the burst ID, and the burst ID is something that well, Alex was showing a little bit of Vertex. I'm actually going to go up here and open up and just show you if you want to, for using Opera, using burst ID is really makes it really easy. So I'm going to zoom in on this region right here. You want to set Opera 701, and I want to go back in time. Really, I'm looking. This work is we're going to use the year 2020. Search here, and it's going to show the three scenes that exist. The main one we're going to be using is right here, and if you want to get the burst ID, the burst ID is right, you know, right here. So I've just copied it from there. So that's just a quick example. Anyway, so now I'm going to take what I have here, and I have it print out that it's found 29 images. So what it's looking for is in the year 2020, using this exact burst ID. It has 29 images. And the results appear in this object, or in this class object from the disco search, or maybe it's just a dictionary actually. But anyway, you get, and these results, or no, it is class object. These results have a number of things you can, well, that they do, and you can see you can read up on the documentation. One of the things I just want to show is I'm going to take the first result and print out the properties to it. And this is just maybe to help you, because you might, as you're going through this data, you're going to have to pull certain things out of it. And you're going to have to find some of the metadata that you need. So you can see all the properties here. There's links to various things. There's links to, thumbnail images of it, but there's also the links to where the actual data links. Orbit and path number are useful. Anyway, so that's there. This next cell is just going to download this data. So it doesn't take all that long. I'm going to actually show you. Oh, okay. So right here, it's downloading this data. We have it set to getting all the files in the data, just because to make sure we get both the VV and the VH image. So anyway, book again, but it doesn't take that long to download. Just waiting, it'll say, it says busy right there, it'll go over to being idle. As soon as it does, I'll run the next bit. The way that I go through this, there's a bunch of ways you can do to actually get at the data, but a lot of what this notebook is just how to access the data, how to look at that stack. Okay, so now this next cell, what I do is I create basically an object that has all the metadata I need with the pointing information of that data. And in this case, I'm using a pandas array, or a pandas data frame, which is, I'm calling it stack meta, the metadata for the stack. And for each element in it, I'm putting in a file name for the VV image, a file name for the VH image. I'm getting the date, the exact date of it out. And I'm also looking at, I'm creating something called day of year, which is just a number, that's the decimal number of days since January 1st of that year. And I'm putting it together in this data frame, which here's just a printout and see what it looks like. So it just has the various images for the scene. So, and then going on, so now we have this, so we can actually get at the data. And here's an example of just how to view this data. So I'm using GDAL open, and then read as array. So I'm just reading the GDAL, reading the TIFF file using GDAL to look at the image. And I have, I'm referencing which image. There were 29 in the stack. So that's going in here. In the image type, I have image file CP for copolarized and the image file XP. You can use instead if you want to get the cross-polarized image, which instead for most of my work here, I'm using the copolarized image, the VV image, but some of your applications will need VH images. So anyway, you can play with various things as you want. But also we're looking at time series. So the next cell in this notebook is looking at individual points on the in the image over the time. So basically what I do is I just go iterate over this metadata, and for each image in it, or for each entry in the metadata, I open up the image and then I get the value at one point that's given. So let me show you this, and this is another thing that I will highly encourage you all to play with. So right here, I have a list of potential points we can use right now. We're using this one, and this is at fairly high elevation in the accumulation area. I also, after I print out a time series of this one point, I print out a couple maps just to show where in the image it is. Zoomed in image up here. Everything that's really dark in this image has a really low backscatter, and that's because it's snow that's pretty wet. And so snow that's pretty wet behaves like open water. Josh was showing earlier in his presentation the reflections on how open water causes the signal to bounce away, and you get very low return of the signal back to the satellite. And so we can see the time series here over that year. Let's see, I can see his question. Yeah, the red dot, the red star in the image is where this time series is being drawn from. I have it plotted on the map, so as you look around the map at various points, you can see exactly where the point is being drawn from. Anyway, in here in mid-May, you can see the backscatter sharply decreases sometime in mid-May. And I have other points here that you can look at. So I'm going to uncomment this line, and now my I point and my J point in this image are a little bit different. And we're doing this again. And so now I have a new point that's being looked at, and this is a little bit further down the Black Rapids Glacier. And there's still this dip in backscatter, but maybe it doesn't go on for quite as long into like summer. I have another point that's further down the glacier. This is these red dots here showing the point we're looking at is kind of towards the front of the glacier. And over here, you can see melt is maybe a little bit earlier in the year. It's right before the start of May. And also there's only a couple days, and each of these days are 12 days. Each of these points are 12 days apart. There's only a couple images here where you actually see melt. After that, the snow is melted out, and you just have, it's pretty debris covered here. There's either bare ice or debris cover in this area. So there's snow melt there, and then it goes back. Something, but there's other things in this, and I've had this here. I encourage you to play around. I actually have a line you all can uncomment, and you can just try out random points in the image in I and J if you want it. I'm going to show just one quick example of vegetation. So here's a point that's just has a bunch of vegetation, and there's not maybe as much to see in it, but there's a radar signal. There's maybe a decrease in the radar signal when there's melt. Oh, here's where the image is when snow is melting, and then it's maybe a little bit higher. But for vegetation, we were talking about how cross-polarized images are better for looking at vegetation. So you can change this to a, say, image file XP. It'll bring up the cross-polarized image instead. So that's using the VH. And in the VH image, I do see that the backscatter values are higher during the summer from about early May onward. And I know from experience being here in this area, this time when the backscatter values increase is certainly when I know the trees get their leaves. So I'm not an expert in looking at vegetation with colorimetry, but I know that this increase in backscatter corresponds to my intuition of when trees have their leaves here. So yeah, there's a whole bunch of points you can you can look at, things you can explore in this data. And I would certainly encourage you to keep playing with it. I'm going to move on to continue looking at melt, at snow melt. One of the first things I want to do is I want to get a mask file. And the mask is just so that I'm just that I know when I make plots to only plot places that have data. And so the mask files are files that are included. I'm going to go back into this file structure. You can see all the files in this list. Each of these images is actually brought this file that says mask in. And these opera masks have might be useful for various applications. But they don't just say where there's data and where there's not data. They say where the RTC correction has corrected for shadow effects or layover effects or for both. But for my own work, I only care about areas that is there data, is there no data. And so I'm taking everything that has regardless of whether or not there's shadow or layover corrections. I'm just counting all that. So I'm going to make a quick mask of this area. And then with that, I can go into the actual trying to identify melt. Now, before I had said the algorithm that identifies the onset of melt and snow looks for when does the backscatter drop by 3 decibels below a winter mean value. And this method is primarily for surfaces that are free of vegetation, but it is quite sensitive with snow. Small changes in snow moisture, I mean, even 1% moisture by volume can cause backscatter decreases like this. So in order to run this method, the things that are important here is I have to get out all of the winter images, and I have to actually make the threshold. What is that 3 decibel decrease threshold? Because that's different for each pixel. And so in order to do that, I first have to pull out what are all the images that occur during that winter time period. So I use this stack meta data frame I have, and I use the lock function here on it, which is pretty useful for pandas data frames to just identify where all the images where the date is greater than a winter start date, and all the images where the date is less than a winter end date. And I create that list. And then from there, I set up a map, and I open up, and then I iterate over all of those specific winter images. And one thing about SAR data is these opera images are kind of small. It is possible to work, if you don't have too many of them, you can load them all into memory. But a lot of the SAR images you're going to be working with can be pretty big, especially some of the NISAR data that's coming, but also lots of Sentinel-1 data from other sources. They can be quite large, and so I don't always recommend loading them straight into them all into memory. There are ways to access bigger sets of data using Xarray, using some other tools that might be smarter about handling memory. For myself, I'm going to just load one image at a time. I need a mean value of them. So I'm going to iterate through this. I'm going to load in each single image and just add it together. And then at the end, I'm going to divide by the number of images I have to get a mean value. So I'm going to run this. It says I found 7 winter images. And then I've created this melt threshold map here. And then I have the next cell just plots that that figure. So now that I have a melt threshold, I know I can use it because then I can I can open up any image I have, and I can look and see, is the decibels of each pixel below what this threshold map is? And therefore to see, do I detect melt in each of these images? And so right here, I have, I'm looking at just a few images, and so I have these figures here. Anything that's in yellow is where I do detect melt, and anything that's in purple is no melt. It's just a 0. And I have a set of dates. So so like this image here, these images are, this one is May 7th. And it's showing you see melt in some of the low-lying areas, not yet moving up everywhere. By the May 19th image, there's melt extending to much higher elevations. There's still some areas that don't have melt yet. And then by April 3rd, or by May 30th, you see melt, much higher up. In this final image here, in July 6th, there's still melt in higher areas where there's snow cover there, because there's snow cover on those glaciers that persists there from year to year. That's one of the features that causes a glacier to exist. And there's no melt on other parts of the glacier where the snow has melted out. And in low-lying areas, you don't see melt there. So that's and so that's how I'm using in this. I'm simply taking making an array. I'm comparing this image to is my single image less than this melt threshold to generate each of these. And then the thing for me that's interesting is, okay, well, now that we have this, can we track when the onset of melt was across a big area, not just in single images? And so the way I do that is I'm going to iterate through the entire stack of images again, and I'm basically going to look at when does each pixel go from not having melt to having melt, and then I'm going to identify melt, the start of melt being that point. And I do something a little bit, just a little bit tricky here, but I'm saying the actual start of melt is halfway between the last no melt detection and the first melt detection. That's what this day near mid is. But anyway, all that to say, so at the end of this, I'm able to create a map that says, okay, here's the start, here's the onset of the date of the onset of melt. These are in days since January 1st of that year across the entire region. So that's the output of this work. And I have, I'm not going to spend too much time into this. I think we're probably running a little bit behind now, but there's several other years and other data sets that you can explore. As the other bursts I've provided here were these other bursts in this scene. So I'm going to quickly just show, if we go back up to the top here, I've provided a few others. So if we go to this one, it finds some images, and I can do this again. And the last thing I'll do is I'll just quickly, run through this for a slightly different data set. So I also delete everything that's in the data folder here, just because I don't want to have all of us burdening the system with a ton of data in these, but it's, again, pretty quick to download some of this. So, and you can use this, you can choose any burst you want, but it's takes a second. The beauty of Open Science Lab is that Open Science Lab sits in the same Amazon web environment that the data is in. So when it's downloading the data, it's not transferring it from anywhere external. It's just moving it around within this Amazon area. Oh, yeah, thank you. I should have in chat, I should have brought that up. I'm using this particular area because there's Opera data here. Opera has only had continuous RTC records going on from earlier in 2023. Whereas this is an example somewhere in the past. In the future, you can use Opera data for this work. So yeah, I'm gonna quickly create this image. So now my image has a different geometry. Yeah. Ask, and so I have 7 winner images here. I'm going to just run through this and have show the whole workflow. Is from a different view. Yeah, so now it's a different geometry, and again here you see this similar pattern where melt being detected much later at some of the higher elevation points in the middle of this. And with that, I think I'll bring my bring this example to a close. I think Alex has another example of using time series of RTC with Opera.